Hello everyone, I'm Dr. Liang. In this talks, I will talk about generative models for classification. Focus on some basic classifiers, LDA and QDAs, and then apply them to set one problems. So by the end, you will know when to prefer LDA or QDAs and the reason. So next slide. Um, Here's a plan. First, I will talk about introduce Kikri um, s- to classifications and to paradigms, discrimination and generatives. Then we will cover three key concepts: Bayesian rules, LDA, QDAs. Next, we'll solve problems. So next slide. Introduce. Classification is about predicting a category of level Y from picture S. We can offer either as house level, class level, or posterior properties. The decision's boundary is the surface where the predictive quest change. There are two paradigms. Discrimination methods, one posteriors or decision functions directories. Examples includes this example includes KNN and logistic regressions from generative methods model. The classifier and the class condition densities and then apply Bayes rules. So we obtain the posterior posteriors from class priors and class condition densities. Examples include LDA and QDA. Today, we go deeper on the generative side because it uh, connects directly to set one problems. So first key concepts on Bayesian classifiers. The Bayesian classifiers is the ideas with the class with the largest posteriors properties. So we obtain that posteriors by combine the prior and the class condition density by Bayesian rules. The decision boundary is where two class tied on that space on the decision boundary. The classifier is indifference between them. In practice, we don't know true priors or class condition densities, so we want to estimate them. That's where LDA and QDA come in. Um, LDA, QDA assumes Gaussian distribution and estimate the necessary parameters from data to approximate the Bayesian rules. Next, key concept LDAs. LDA assumes Gaussian class condition distribution with a shared covariance across cross. The same covariance across the cross. Because of the shared same covariance, the resulting decisions boundary is linear. Um, as the equation below shows, it is linear. Anyways, on the trace set, LDA lower parameters lower flexible, so it's typically avoid overfitting. On the test set, LDA is strong when the two boundary is non-linear, so when data are limited. This is a classic lower variance advantage. It can struggle, but however, it can struggle if covariance to deeper or the boundary is curved it's introduced because of bias or their bias. Next page, key concepts, QDAs. QDAs is also Gaussian, but it's Um, but it have different class-specific covariance for class. In other words, covariance is different for class that build a quadratic decision boundary, orbit decision boundary. On the train set, QTA is more flexible and usually achieve low train error than LDAs, but with a small n or higher dimension piece, estimating separate covariance can be unstable, increase variance and over victories. But enough sample, it is best. On the test set, QTAs shine when the true ground truth boundary is non-linear or its covariance differs. Mm. If bias is lower than LDAs, um, as the train sample size grows, its variance come down and generalization improve. The next slide is um, I'll solve the problems 8. Problem 8, if a Bayesian decision boundary is linear on whose wins? UDA's wins or LDA's wins. So I said about train set and test set. In train set, QDA usually achieve lower train errors because it's more flexible and fit the data more tightly. Um, but test sets, RDA is typically better. Why? With a linear ground. Uh, why? Mm, With the linear ground truth boundaries, LDA is simpler and collects shares models, so it has lower barriers. So and QDA instead in on other side of QDAs estimate most convenience parameters with invite overbiddings with big data. And in addition, when sample n is infinite, um, QDA and LDA, both QDA and LDA is equals because Bayesian rules. So LDA is typically better. Um, um, so next slide, problem B. Um, if the Bayesian boundary is non-linear, um, in train set, QDAs, um, as I said before, so QDA is more flexible because more parameters. So QDAs lower train errors. On the test set, Bayesian decision boundary is non-linear. QDA usually win. Um, um, I say recent LDA shares various linear boundary uh, um, um, LDA as I said before, LDA just shares same for various, but QDA has a different for various for class. So is lower bias on the non-truth. So um, but with a small n or large piece, um, QTA can outperforms because high or variance. Next slide. Problem 6. Um, as the sample size n is increased, what happened? Which is um, my answer. QDA improves more than LDAs. Um, s- um, to explain the reason, um, QDA are more have more parameters and more flexible. So um, s- as sample is increase, covariance estimates tables and variance decrease. The QDA's generalizations catch ups and may suppress idea. Um, in other words, QDA starts with a variance disadvantage because it estimates more parameters, but as and growth, covariance estimate stabilize, variance decrease, and QDA generation catch up and may suppress. Um, and in the truth is linear, the gap shrink towards zeros. Both methods approach the Bayesian rules. Binaries, problem B, D. True or false problem. Um, mm, the test, even with the linear Bayesian boundary, QDA probably have a better test error because my answer is both. Because QDA can represent a linear boundary if a sample is enough, but it pay a lot of variance costs from estimating separate covariance. And if sample is finite, limited, the cost usually outweigh and any benefit, so LDA typically has equal or lower test errors. Uh, yes, next, Bayesian classifier, the ideal rules derive from higher and class condition densities. Um, so define the decision boundary postulates. So LDAs with a share covariance, so linear boundary, fewer parameters, so low variance, and have lower bias model problems. So, but when decision boundary is linear and samples same sample and is small, it is small. And QTAs have different covariance per class. So um, it have quadratic boundaries, lower bias. Um, so it is strong when non-linear case with enough data. So um, thank you.